Hello, welcome to this video. In this video, let us compare Otto, diesel and dual combustion cycles. Now, let us consider for a same compression ratio and heat addition, we can compare these cycles. In order to compare these cycles, let us start with PV and TS diagram. We know that for a same compression ratio and heat addition, we will start with PV and TS diagram. Okay. So, pressure versus volume, temperature versus entropy. Let us start with an Otto cycle. Now, we know that Otto cycle starts like a reversible adiabatic compression, let us say it is 1 to 2. Then we have constant volume heat addition. Constant volume looks like this in a PV plot. Then is constant volume heat addition. Then again reversible adiabatic expansion. Reversible adiabatic expansion. Okay, 3 to 4. Then we will have this heat rejection at constant volume. This is our Otto cycle. Okay. Now we can write 1, 2, 3, 4, 1 is our Otto cycle. Okay. So similarly we can draw a TS diagram as well. How does TS diagram looks like? We know that TS diagram 1 to 2 is reversible adiabatic. So, adiabatic process is isentropic process, reversible adiabatic, entropy remains constant. So, 1 to 2 would look like this. Then 2 to 3 is constant volume. So, this is constant volume. This is our PV power gamma constant. This is again PV power gamma constant. This is again volume constant, heat rejection. Alright, this is our heat rejection in Otto cycle. This is our heat supplied in Otto cycle. Okay. Then 2 to 3 is constant volume heat addition. Then 3 to 4 is again reversible adiabatic. Okay. So, that is isentropic process. So, this is 3 to 4. Then 4 to 1 constant volume heat rejection. Okay. Now, just we will extend this line because we need it for knowing what is heat rejection. So, I just say that, so if we extend this line just for the sake of understanding, so let us extend these lines, because area under that curve is not part of the cycle, we just extend this just to know that heat rejection quantity. So, let us call this as 5 and 6. Okay. So, now let us go for same compression ratio. The moment I say same compression ratio, we know that compression ratio is given by V1 by V2, all right. Compression ratio is this total volume divided by this clearance volume is compression ratio. So, in order to keep the same compression ratio, we know that this has to be same. So, we must draw one more on the same plot, that is we will go for dual combustion cycle, then we will go for diesel cycle. So, dual combustion is what? So, part of it I will just choose the other color. Part of it is constant volume, heat addition is happening at constant volume, and part of the heat addition is happening at constant pressure. So, it will be something like from 1 to 2 is same because compression ratios remain same. Then we will have from 2, we will go for 2 to 2 dash is constant volume heat addition for a dual cycle, and 2 dash to 3 dash is constant pressure heat addition. Then we will write in parallel to this line. So, same compression ratio, so it must come to the same volume, okay, in parallel to this. So, let us call this as 4 dash and let us join this line. Okay. Now, similarly, here also we will write it 1 to 2 is compression, 2 to 2 dash is constant volume heat addition, all right. Then 2 dash to 3 dash is constant pressure. Now, this is constant pressure line. So, it is deviated from this point. So, 3 to 2 dash to 3 dash. Now, 3 dash to 4 dash is again expansion reversible adiabatic. Now, 4 dash to this point, that is, this was 4 actually. So, it is correct. Now, very important, we are trying to maintain compression ratio as constant that can be seen in PV diagram. So, volume ratios V1 by V2 is compression ratio. We are trying to keep same compression ratio that can be seen in PV diagram. Similarly, the amount of heat addition same can be seen in TS diagram. Now, if you understand TS diagram correctly, what is a TS diagram? In a TS diagram, we know that Q is given by temperature multiplied by change in entropy, all right. So, in a TS plot, area under this curve represents heat transfer. If you have some curve like this, now area under the curve represents heat transfer in a TS diagram. Now, if you see the area under the curve, let us say heat supplied, right? Heat supplied is what? 2 to 3. For Otto cycle, we can say that heat supplied is area under curve 2 to 3. Now, let us go for cycle 1, 2 dash, 3 dash, 4 dash and 1. Now, this is what we call it as dual cycle. Okay. Now, for dual cycle, heat supplied is area under curve 2, 2 dash and 3 dash. Now, if you see compared to these two, this much area is reduced, all right. So, for dual cycle this much area is reduced, that means that much of heat transfer is reduced, but that is taken care by moving the cycle towards right, all right. So, how much we should move? Such a way that area under the 2 to 3 and area under 2, 2 dash, 3 dash must be same. That is how much it is moved towards the right side. So, that is how we are trying to keep area under the curve or heat addition same, all right. So, we are trying to keep heat addition same. So, we have moved it at a constant pressure. If it moves toward the same quantity of what is lost in this area, then we can have same heat addition, all right. Now, let us go for diesel cycle. Now, what is a diesel cycle? Diesel cycle is 1 to 2 is same, that is same compression ratio, and then heat addition happens at a constant pressure. Now, for a constant pressure cycle, we must start from here and we will have a constant pressure process here. So, this is constant pressure process. Okay. Now, constant pressure process, then again it is parallel to this line. This will be 4 double dash, this will be 3 double dash. Okay. So, this will be similarly, we can start from here. From here, we must go like 1 to 2 is compression. From 2, we must move towards parallel to constant pressure line. Now, this is our 3 double dash, 4 double dash. Then we will join it to the same line. Okay. So, this part is here. Now, 4 double dash. Now, we have moved it again towards right such a way that the heat addition remains same. So, whatever area which is lost here is compensated by moving the plot towards right. So, such that area under the curve of heat transfer or heat addition remains same. Such a way that we are trying to make heat addition same, as well as compression ratio we have maintained same, that can be seen in PV plot. Heat addition remains same, that can be seen in TS plot. Now, just for the comparison sake, I will just draw this. I will just draw this lines. Okay. So, those lines are representation of heat rejection. I will talk about that now. Okay. So, let me call this as a 6 dash, this as 6 dash, this as 6 double dash. Okay. Now, before that, what is this cycle? Let us write this cycle. That is 1, 2, 3 double dash, 4 double dash, 1 is a Diesel cycle. All right. Now, Diesel cycle heat supplied, we can see QS is area under curve 2 and 3 double dash. Okay. We have moved it, but these areas are drawn in such a way that area under 2 to 3, area under 2 dash, 3 dash, 2, 3 double dash are same. So, we have moved it to the right side. So, if we calculate this area and this area remains same, this excess area which is there in Otto cycle is compensated in this right side portion. All right. Now, let us go for comparison of efficiencies of cycle for same compression ratio and heat addition. Now we know that efficiency is given by what? Efficiency is 1 minus efficiency is given by efficiency of the cycle is given by work net by heat supplied. Work net is QS minus QR by QS, or we can say 1 minus QR by QS. All right. Now, if you look at this, if this is 0, obviously this will be 100%, because we are going to multiply this equation by 100. All right. Now, if this term reduces, if this term second term reduces, efficiency increases. All right. How do you say that this second term should reduce? Numerator, if it reduces, efficiency increases. If heat rejection reduces, efficiency increases. If heat supplied is increased, efficiency decreases for the same values. All right. Now, what we can say, heat supplied is same. So, we can say that this term we can eliminate, heat supplied is same. So, for same heat supplied, we can concentrate on this term. Whichever plot has got lesser heat rejection, that will have highest efficiency. Now, let us concentrate on heat rejection. Now, if you look at this, 4 to 1 or 4 dash to 1 or 4 double dash to 1 represents heat rejection. Now, look at this. For Otto cycle, this is the amount of heat rejection. Okay. Now, I will write here also, heat rejection for Otto cycle is area under curve 4 to 1. Now, similarly, heat rejection for dual cycle is area under curve 4 dash to 1. Now, similarly, heat rejection for diesel cycle is area under curve 4 double dash to 1. Okay. This is the amount of heat rejection for same amount of heat supplied. Now, we can conclude which will have more efficiency, the one which has lesser heat rejection will have more efficiency. If you see here, area under 1 to 4 to 1, if you look at that area under the curve, that is Otto cycle. Otto cycle has less heat rejection for the same heat addition and same compression ratio. So, therefore, we can conclude that efficiency of Otto cycle will be higher, okay, because heat rejection is lesser. Then comes dual cycle and then comes diesel cycle. Now, this has to be true only when we are talking about for same compression ratio and same heat addition, we can conclude that efficiency of Otto cycle will be greater than efficiency of dual and it will be greater than efficiency of diesel cycle. Okay. Thank you.